Hi, thanks for having me, inviting me to talk. Anita invited me to talk, and she's not here, but I'm assuming she's at home in cyberspace somewhere watching. I didn't know I was giving a talk to NRP as well as Fabric until recently, so that's fine. But it did make me want to adjust my slides a little bit, and I also did not appreciate until I came and watched some of the talks just how much focus there is on AI and ML. In this room, there's hardly any oxygen left. Well, you would think I would know because I do read the CACM, and that's true of the CACM magazine too. So AI and ML is really captivating a lot of our attention and energy, and I guess we're hoping funding for the next decade. So I adjusted my talk a little bit, trying to be more useful to the audience here. And even though I will talk about the MSRI project, which Fabric is also in the MSRI, we have an MSRI design project that's called Designing a Global Measurement Infrastructure to Improve Internet Security. And I wanted to give you a sense of what's going on with that project. What is that project trying to do? What is that project actually managing to do? What does it hope to do in the future? But so much of that project, as I listened to the talks yesterday, is relevant to those who are trying to deploy and use AI and ML models that I sort of sprinkled in some slides on how this can help you now, I hope, how you can help us help you in the future. And I hope in the end, we'll have some discussion about what you think and what you would like to see. Here we go. So what do I want you to get out of this talk? I do want you to understand the state of what is currently available to study the global internet, to do science on the global internet infrastructure. So I don't mean Facebook, although that's great to do science on that, but I mean the plumbing. I mean the transport systems. I'll talk about what I mean in a couple slides too, the next few slides, but the routing system, the naming system, even the certificate transparency system, the systems that we take for granted that are the only way we can trust that a packet gets from point A to point B, and it's really getting from point A to the point B that we think it's getting to. I'll talk about the current state of the data, operational challenges in collecting the data, tools that are useful to networking researchers or AI researchers, and there'll be some invitation for how you can help. First, why do I think that data on the internet infrastructure should play a key role in AI, the latest AI wave? First, I think we should ask ourselves, what is different about this AI wave from the 80s or the 70s? And I know that people in this room might say, it's the GPUs. That is not what I would say. And that is not what Peter Denning says in the CACM of this month. The core of these models is the internet. Everything on these models works because they could get data freely off the internet. In fact, the Copyright Office is having not a field day dealing with all of this now. All of the copyright offices and the companies that are being sued. So it is the freely available data on the internet and the underlying infrastructure on the internet that has enabled AI. Now, I know NVIDIA likes to say it's the GPUs, and I'm not denying the GPUs are critical. They call the GPUs the gold of AI. But I went and asked the AI itself last night because one of my program managers said, why don't you get ChatGPT to help you make your slides if you're so stressed out about them? And so I asked ChatGPT this question. First I asked 3.5, and then I asked 4. I said, if GPUs are the gold, what is the internet to AI? And so GPT-4, although I had to give it 2 chances to get this right, GPT-4 thinks the internet is oxygen of AI. Now, first it said silicon, and then we said, is there any other element of the periodic table that you would like to propose as a candidate for what the internet is to AI? And it said, well, oxygen might be a good match. Fundamental life-sustaining environment that gives the rise to AI, this wave of AI. The effectiveness of this wave of AI, I would say. I mean, I would say there's more justification for the hype this time than there was the last few times. I was an undergrad for the last big wave in the 80s. That's how old I am. Not as much hype as we're giving it, but it's definitely merits some attention, right? So the internet is not just the foundation of AI. The internet is the foundation of everything that we're doing. And yet, we actually still to this day, perhaps even more so than before, because the internet is growing even faster than our interest in AI, we have little understanding of the internet as an infrastructure. What keeps it stable? What makes it not stable when it doesn't get stable? What are the vulnerabilities out there? Just of the infrastructure. I'm not talking about Facebook. I don't mean to bang on Facebook. I'm not talking about the application layer. I'm talking about the transport layers. There are multiple of them. And yet internet security, despite being one of the most important challenges of our time, and all of the documents coming out of the government attest to this, there's not really even a discipline of this for very good reasons. I'm not going to go into that. That's another talk. But what can we do that is relevant to the AI, the current wave of AI? We can actually create data sets. We can create data sets that are labeled. They might not be labeled as well as we want, and that will be a theme of my talk, because that is really hard, and that is where the technologists can't do it all on their own, and that is where even NSF funding, no matter how much you throw at it, is not enough to do it. We're going to have to confront that problem. We are confronting that problem. We have confronted that problem, but we should put it front and center, especially since Katie said at our keynote yesterday, which I very much enjoyed. But it's clear that data, the focus on data is coming. And there is great recognition that this is a really complicated problem. Data governance, trustworthiness in data, it's a problem, and it's not a technical problem. It's not a purely technical problem. Certainly the solutions will involve major technical innovations. So why else do I think data should be critical front and center in this next wave of AI, including how the infrastructures you all want to support it? It's compatible with a national priority to train STEM students. It's very hard to get good data to STEM students because most of the data that's really interesting is owned by companies. So one of the things that we really do for students is we give them macroscopic global data sets about a critical infrastructure that are free, openly available, and hard to understand. So I will also say that like many fields, like all fields, there's a lot of problems in our field that are ripe for AI solutions. That does not mean it's low fruit on the tree, but it's something to pay attention to. So what are the gaps to these better solutions, these transformative solutions to problems that use AI? How can we reduce the barriers to actually solving these problems? We need better labeled data. We need more comprehensive data set. I'm going to talk about vantage points to get better pictures of the global internet infrastructure. We need ways to find the data, because sometimes there's data out there that it's very difficult for students or researchers to find. And then interpreting and validating the data, even harder. And that goes along with labeling, but it's another level. We also need open technology that researchers can use, including LLM models we can train. I loved Vince's talks yesterday. I was like, oh. And Frank had warned me, my director, if we can't do it ourselves, we'll go get Frank to give us his LLM, or let us. But now SCSE is helping us do it ourselves. I'll get to that toward the end of the talk. So measurement infrastructures, reliable data sets, advanced tools to process these data sets are challenging to create and sustain. Now, why is this problem going on for so long? It's been 40 years. We can't get the internet right? Okay, first of all, this is not a problem the market's going to handle. And there's increasing recognition of this. What is the focus of internet security in the market? It's the enterprise. They have money. They will pay for it. There is incentive there. In the meantime, who protects the core? Hint, compare it to other critical infrastructures like the roads or the water or the climate. The internet is different right now. And here's another way the internet's different. It was a research project that escaped from the lab. In fact, it was one of the research projects funded like ours is that escaped from the lab because it was amazing. But every core transport service of the internet, addressing the IP layer, just handing out addresses, naming, routing, has well-known vulnerabilities. So I'm going to talk about that on the next slide. So now there is recognition after many decades of trying to retrofit some security onto these layers to try to mitigate these vulnerabilities that data is going to be a big part of the way forward, transparency and accountability of how the infrastructure is used. What does that mean? We have to go back to all our problems with collecting data. It's expensive, it's complex, there's misaligned incentives, there's privacy issues to deal with, commercial sensitivities. Privacy PII, privacy commercial sensitivities, two different but both very important aspects of privacy. Just to drill down, for those of you who don't remember or like to put this out of your mind, because if you didn't, you wouldn't sleep well at night, like I don't. Every layer of the internet, from the IP address you put in the packet to the mapping from the host name to the IP address that you actually go to when you type in apple.com, every single layer in there can be subverted fairly easily. Like there is no mechanism for authentication in the protocols that says the IP address in the source of the packet I just accepted onto my network that might have malware in it is actually the IP address that it came from. Nothing checks. Not in the protocol, wasn't important. There's a much more complicated story than that. But for now, the routing system, really, there's nothing in the protocol that prevents anybody from announcing my address space and saying, I am UCSD. And there's also nothing in the protocols right now. This is built in. Folks are trying to build in some layers after the fact to try to create that accountability. Like, in order for me to be able to trust the IP addresses are really the announcements in the routing system are coming from the place I think they're coming from, there has to be a layer of ground truth. Like, how do I know where they're actually supposed to come from? And then check what I'm receiving against what I know. Domain name system, same thing. There's all sorts of ways the DNS mapping, getting from apple.com to the IP address for apple.com can go wrong. It is such a complex space. So I'm actually not going to talk about this very much today, but I'll mention a few things that we're trying to do to address it. And the certificate authority system put in place to try to address some of the other problems also can be subverted. It's almost like this whole architecture was designed to facilitate propagation of misinformation. Okay, so what do we do? Well, this is our MSRI. We have a design project going on. It's in its third year now of what's going to be four years to secure the internet, to gather data, design global measurement infrastructure, to support research on the global internet infrastructure. We had the obligatory broader impact, intellectual merit. All of these, I think, are playing themselves out. I'm not going to spend too much time on that. The focal points here, and now I'm going to spend the rest of the talk on these 4 types of data. We're driven by, we spent a year assessing what are the harms that are really out there. What are the data that people use right now to inform the harms, to assess whether they're happening, to mitigate the harms? What are the problems with the mitigations, and what are the data that is used for the address whether the mitigations are working? All that. We went turtles all the way down. We did a deep dive on this, and the working document, because it's a bit of a living document here, the field is moving, is online on our website. So I'm going to focus on the following types of data: active measurement, routing data, passive traffic capture data, and DNS data. Now, this will be a bit at lightning speed, but I won't be able to go over everything. But just to give you an overview, and then I'll make the slides available, because I think maybe a handful of you are interested in any one of these. So there'll be something in here for everyone, but then a lot of email might get done for the rest of this. So I'm going to talk about 4 types of data: active, routing, traffic, DNS. And approximately in the order, this is an oversimplification of how much cooperation you need from the rest of the internet, the owners of the infrastructure, the owners of the data, to get access to this data. So active measurement, you put a host up, it starts sending traffic out, you make inferences based on what you get back. I can do that myself. I can do that from this laptop right here. I don't get maybe a full view of the internet, but I can do it, and I can do it without permission from anyone. If I want to do it from 1,000 places, that's a different story. So there's a dimension of scale that's going to require more cooperation from many people and more work and investment and all of that. And then there's just fundamentally the type of data that you're collecting. Traffic data, way harder to get. Again, I can do a TCP dump on my laptop just to get some PCAPs coming on my laptop. But if I want data on a link that is relevant to the global internet, that's a really challenging problem. And then DNS data, there's so many types of DNS data. But the DNS data that is the most salient for security research is, who do we think owns that domain name? Because it seems to be malware. That's hard data to get. It's been made harder by policy innovations, but we'll talk about that. Actually, we won't talk about that. I'll talk about that offline if you want. All right, so, we have, active measurement is what we've probably spent the most time on, because the part about not requiring cooperation. So we deployed nodes all around the world, global internet. Actually, we've done this for many, many years before the MSRI project. I'll talk a little bit about what happened during the MSRI. What we've made it now is, as part of this MSRI, we're designing more programmability, software programmability into this platform to support complex internet measurement experiments that you can't do anywhere else. There are other measurement platforms out there, like Ripe Atlas is a fantastic measurement platform, 10,000 nodes. Very simple measurements can you do from this platform. You can't do complex measurements. There's also the cloud, which you can do whatever you want, whatever is in the TNC. And if you want to pay for egress, measuring the whole internet can get pricey if you're paying per bit. But it only gives you cloud vantage points. So there's this point in the middle where we'd like to get many vantage points representative of the global internet. We'd like to be able to do complex experiments. And so this is our navigating this trade-off. As in the cooperation matrix I just showed you, if you just think about active measurements, there's a very similar kind of matrix on, or similar kind of spectrum on, what am I going to be allowed to do on the node? Because Ripe Atlas can get 10,000 nodes deployed because they can commit to those hosting sites. They're going to do 3 things. They're going to do ping, they're going to do traceroute, they're going to do maybe DNS lookups. That is limiting for network research, especially for network security research. It's great for operational reachability, which is really the market for Ripe Atlas. The researchers sort of coming along for the ride. I'm not knocking that. That's a fantastic way for researchers to get access to data. That's probably the most successful infrastructures we've ever had, or that model. So what we're trying to do, is operate in the middle sweet spot here, where we want to enable researchers to do complex things on the nodes. We don't want them to have to program the complex things, not only because they don't want to do it, they really want someone else to do it, but also because therein lies dragons. So we are creating this, what we call a domain-specific language. Why is that coming later? Okay, I'm going to reverse the order of these slides. To provide this programmability. So this was after several workshops and many meetings with community about what they would like to see an active measurement infrastructure do. What are sort of the primitives they want this DSL to provide? So it does provide all the basic ping, traceroute, DNS queries, also HTTP. Now HTTP queries, like you might want to know what is on the other side of this port 80 or port 443 connection. And there are sensitivities with even an HTTP connection. You would be surprised. But Ripe Atlas, for example, has nodes in Iran, where an HTTP lookup to just anything, not a good idea for a node in Iran. So that balancing that, scale, scope, capability of the vantage point, not always technical in nature, is part of this project. So let me go back, and there's our obligatory architecture diagram. Ilkay says she likes complicated architecture diagrams. This one is for Ilkay. It's not that complicated. But basically what we do is providing classes and methods to interact with processes on the nodes from a centralized vantage point. So at the moment you log into or get an access to our centralized vantage points, it allows you to send commands to all these nodes through this language. We've got documentation up there, that's this, and some blog entries describing what we're doing. We're writing a paper on this, but we wanted to get this out there for people first to use. Okay, and then let me talk about this. One of the challenges here, this is a graph of the number of VPs we have. Can you find 2 retirements of senior personnel in this graph? Yes. Can you find the start of the MSRI design project where we decided we can't just keep this thing on life support. We have to stop saving the nodes, go redesign, automation, DevOps, all of that, and then we'll restart and we'll bring them all back and we'll get a bunch of new ones. You can see it all. Anthropology in measurement data. So what are the problems? You guys all know these problems. I mean, I have 4 slides on this for each type of data, but there's a lot of repetition here because you guys all know this. It's incentivizing people to host infrastructure. It's automation, sysadmin, DevOps, idiosyncrasies. In this case, a lot of idiosyncrasies with individual nodes. They're in someone's house. They're in an IXP. They're in a business. The person has varying levels of technical capability, even the same person that they were last year, or that person's gone and no one even knows what the node is you're talking about anymore. So this is a operational risk of this mode of crowdsourcing volunteering infrastructure. Okay, I talked about that. Then we do a bunch of other tools to support access to vantage points we can't get. That's what Periscope is. To support navigation of the data, because now we have terabytes of traceroute data that we're constantly running in the background, in addition to trying to run other people's measurements. So you need to be able to navigate all of that data and extract the data that you actually want, rather than having to mess with 10 terabytes of data every time you want to do an analysis. And tons of derivative data sets that we provide through this catalog, that I'm going to keep coming back to this catalog, because one of the challenges I mentioned earlier is students getting access to the data, finding the data they want, and then finding out, well, who else did what on this data? Like, has AI already been done on this data? What did people find? So I'm going to talk about that too. It's a under-attended problem, I think. How you can help with this? This is one area where you can definitely help right now. You can help us deploy VPs. We've now, because of the new redesign, we have software-based VPs, including container-based VPs, as well as we can give you a Raspberry Pi if needed. You can develop your own. We're actually experimenting with deploying a one-use server type thing at an IXP so that we can get all of the peers at the IXP to be instant vantage points. Think of it as like hundreds of vantage points for the price of one, or the hardware price of one. There's still lots of peering price going on there, but that's one of our, attempt to do innovation in this space of getting access to vantage points. And there are some details there about the memorandum of cooperation. Why should you do it? How do you help? And then, I see, these are popping up. And then we have a bunch of research that's happened over the last few years. I mean, this infrastructure has been around a while, but just some subsample. Most of these not our own work, but work that we're helping the community do. And as you all know, that's the hardest part of operating infrastructure, is getting people who don't know about the infrastructure to use it usefully. Okay, so now I'm going to switch from active measurement, which is really a broad category of measurements. You can ask the internet a lot of things that you can send packets to the internet that will allow you to infer a lot of properties, including security-related properties. And that's the focus of the active measurement infrastructure that we deploy. For routing data, you need more cooperation with ISPs. And you need routing data sometimes to interpret the active measurement data, like what network owns that IP address that I think I'm transiting over, or what network do I think owns it? So you need BGP data for that. That BGP stands for Border Gateway Protocol. I'm assuming you guys know this. I don't have to go into detail because you guys all operate networks or work with people that do. But that's the, if the internet is the oxygen of AI, BGP is the central nervous system of the internet, right? It's how you communicate connectivity. So again, I could set up a router. Maybe my mom couldn't. My mom could do the active measurement herself. She probably does it because I taught her how, but she can't do BGP. But a big number of us could do BGP from one place. Much harder to do it from many places. And then much harder to do it from many places to many places. And so we have oops, this one should have been first. Sorry. Some of these slides were done very late. But I'm going to skip this slide anyway because you guys know all of the problems that can happen with BGP, and I mentioned it earlier. You can send an announcement that says, I am the person I'm not. It's amazing that we're still using this as our infrastructure. So, and we've tried, and are still trying, and having some success with fitting some layers of security for some aspects into the deployment, but it's very challenging. So it's clear that measurements are going to be the future of routing security. Global, public measurements that provide a layer of transparency and accountability for the routing system. Now, what did I skip? Nope. Okay, because I didn't skip. Okay. Oh, yeah. 2 approaches to gathering BGP data. Not ours, by the way. These are operator-driven. Operators actually need to know what the heck their network looks like from across the internet so they can debug things. They can debug connectivity. So operators 20-some years ago set up these things called route collectors, where they would just take a router and peer with anybody who wanted to peer with them on that router. And you can do this without having the other router next to you, although it's best if the other router is next to you. That's like how real peering happens at exchange points. So these guys have these 2 projects. RouteViews is based at University of Oregon, NSRC, partners in our MSRI project. And RipeRIS is based in Europe, part of the RAR in Europe. And they both set up collectors at different exchange points, and then each collector peers with many dozens of other ISPs. All volunteer, opt-in, helps the operators. And then they collect MRT. MRT is a data format for BGP data. It's not important. But they collect snapshots. They collect every update. So the routing tables are essentially continuously updated by every router based on what you're hearing, announcements of links going down, et cetera. They allow streaming support for the data. We've actually built some tools many years ago to support some streaming analytics coming out of the 2 data sources. And then they also, RIPE in particular, provides a lot of metadata to allow you to interpret the data, like who is, because they are the ones, in fact, that hand out the IP addresses, so they actually know to some extent who owns them. So they can provide a lot of useful metadata. So what are the challenges with this kind of data? Well, same thing. You got to get people to deploy infrastructure now, and not in their house. You've got to get people to give you space in a IXP. That stuff goes for money nowadays, and power. Oh my God! So and all of this is crowdsourced volunteer crowdsourced on both, and they are hitting scalability limitations too, and they have some data quality issues, as all data sets do. And there's limited resources to really do data integrity checks and manage the pollution that inevitably creeps into data sets. RouteViews has put every update into BigQuery, partly as backup, because it's now a 26, maybe 27, God, we're all getting older, 26-year data set of BGP updates on the internet, and they don't want to lose it. So they're putting it as many places they can put it. It's all public data, so no problem with private sensitivity. In fact, they've talked to Frank about putting it into OSDF. There's a looming challenge here. Fewer than 1% of ASs on the internet, about 80,000 ASs on the internet, are peering with any one of these collectors. That's a small number. Now, many ASs, you might argue, okay, they're small. That's like Joe Bob's garage. Why does he have an AS? An AS is the unit of communication in BGP. It means network. It means autonomous system. But even if you count the bigger guys, the guys that provide transit service to someone, it's less than 8%, or it's around 8%. So it's a snapshot of the internet. It's a considerable snapshot. It's not like an 8% because many of the transit providers see redundant connectivity. But it has now been demonstrated in academic papers that BGP hijacks can circumvent the measurement infrastructure. Like knowing the visibility and measurement infrastructure, you can engineer around it. So that's a problem. Because what really it means is that we have to scale these infrastructures. We have to scale this mode of data collection up by an order of magnitude, at least. And there's some researchers that have been saying that for some time. So that's what we tried to design in the last year. We worked with some folks in Europe that have a little advisory committee of folks from RIPE and RouteView. So all of this is in collaboration with them. They're busy trying to keep the lights on with their infrastructures, so they're very eager to see what exactly we managed to do. Now, there's no free lunch here, so there's a trade-off. What RIPE and RouteView, these two big BGP services, do is they collect every update they see coming in, an extraordinary amount of that. Like I would argue 80% or more, but there's an empirical question there. They've done some of this analysis in the paper, is redundant information, meaning I get the same update from two peers, maybe two peers from the same data center. Now, there's a debate to be had, an epistemological debate about what means redundant. Because if I do get two updates from the same peer about a link, there's a little bit of not redundant information in there that I got it from two different peers, right? So there's sacrifices will be made. Compromises will be made if you really want to optimize for, look at this lower right graph down here, if you gather all the data, how many, the really tricky kind of links that do not propagate up to transit, through transit links, how many do you see? How many can you actually observe with a given number of vantage points? Or if you take a random selection, which is what we find researchers are doing. If you look at the literature, researchers are not looking at all of the data because it's too much data for them, especially if the paper deadline is in a week and they don't have access to Expanse. So what they do is they pick a random one, or they pick a random 10, or they pick the one with the most of data. And in fact, these Strasbourg folks have done another great paper on how to pick the best one. If you can only pick one, they have this thing called MVP, Most Valuable Peer. But what they show in GIL is the name of this platform, GILnet. Well, what am I doing? Is that you can just take a GIL deployment with they had to simulate this. This thing doesn't exist yet, but they can simulate if you had 50% of ASs peering with GIL, you would only store, if you're willing to throw away some level of redundancy data, you could only store a very small fraction, would allow you to scale to orders of magnitude more peers, to get the peering data, get the interconnection information that's not redundant, and reveal links you just can't see if you just take a random subset. Here's the website. One of the little asks at the end here is go peer with this if you are in control of a router and you're willing to peer with something experimental. It's all automated. And then we have other tools like the active measurement and traceroute. Now you've got terabytes of BGP data. What the heck? So we have we built a graphical interface. We designed it. This is still prototypey, but you can go there. And to allow you to select a specific set of BGP data from route views based on network or prefix, address prefix, or community, BGP community, a tag that some of you know about, but most of you probably don't. And please do not learn about them. And you can just get the subset of data that you care about. And then we have also had for 20 years or so this analytics system that takes the BGP data and does analysis, because what many researchers really want is just tell me the answer. Tell me who's connected to who in what way, so I can go study routing algorithms on a realistic internet topology. I don't need to redo all this stuff. You do it for me. Maybe I don't trust exactly everything you've done. There's errors, but it's the best thing out there. So let's move on. So that's what we have. We have a ranking, a system where we infer all these routing relationships. Heuristic, AI would help with this, I think. Or I should say LLMs could help with this. I'm sure someone's working on that for the IMC deadline in 8 weeks. And then we rank ASs according to what we infer to be their customer codes. So sort of their routing footprint on the internet. All right, and then we have some other tools I mentioned earlier for streaming. I'm going to skip over for streaming data, for reconstructing routing tables. This is kind of esoteric in the weeds. And then we've got lots of BGP-derived data sets, labeled, annotated, with things that researchers have said, this is what we care about. We need something that very quickly maps an IP address to the network that owns it. Maybe there's errors. It's all, if you can make it all transparent, the algorithm you're doing it, fine, we'll take it. So we do all of that. And then we've got lots of people using all of these data sources. So lots more data. Here's how you get access to the BGP to go, we call it right now. Other BGP data, other BGP tools. How you can help? You can peer with route views. That would be great. Or RIS, or both. You can also peer with our new experimental thing, which has very few peers, but you can go to this thing right now and maybe Matt will do it during the talk. He's doing it right now. Now, we've already talked to Internet 2 about this, by the way. There's a little bit of an issue there. You probably know about it. Okay, traffic. So I'm running out of time here. But So I'm just going to go really quickly. Traffic could be its own talk. It's the most complicated. It's got the most privacy sensitivities. We heard a little bit about it yesterday. What do you mean by traffic? Is it just the number of bytes? That's a lot less sensitive than the IP address in the bytes. So we've done a lot with traffic over the years. We have this thing called a dark net, which on the less sensitive side in terms of privacy, because it's traffic that shouldn't be on the internet. It's traffic from typically malware trying to spread or other sort of malfeasance trying to spread to random addresses because it's mostly unused space that we listen to, unused address space. So we provide access to this data a number of ways. We try to label this data so that researchers don't have to figure it all out themselves. And we try to develop techniques that allow you to gather enough insight from the time series from like the statistics of the data that you don't have to go to the PCAPs. But you can use this high-level analysis to tell you which packet captures to go to or which intermediate flow data to go to. All right, so I'm going to skip what are the challenges. In this case, the challenge is different from the other. Traffic data is so expensive to maintain. In fact, the only reason we have like 15 years of every PCAP coming into this rather large chunk of address space that is someone's allowing us to monitor, it's not ours, is that the DOE, if in here, thank you, NERSC allowed us to store it up there for free. So they have like 15 years of PCAPs of pollution traffic on the internet. But turns out pollution is really useful for security research, and DoD has taken an interest in this data. So we're spending a lot of time trying to, again, create derivative data sets that shorten the time to insight, as they would say, of the researchers. So I'm going to skip over that. Now, there's also a new approach that we've designed that actually turned into a CI/CI project, PI meeting next week, shout out to Kevin, that Ricky, one of our PIs at CADA, is developing to try to, this is still in the line of making the data coming out of these dark nets more actionable to people that operate networks. So thank goodness SDSC volunteered to be our first network. So we're going to take the telescope data that we have, set up a telescope-ish kind of thing, that is traffic coming into IP addresses that are not assigned on SDSC's network, and compare the intelligence that we can gather from both and use one to inform the other, really use the telescope to inform operational threats at SDSC. And we would love it. If other people wanted to deploy this too, you may want to wait for us to get a little further along. We're still waiting for hardware to come in. But all of this open, the proposal's up online, et cetera. I'm going to skip this part we did in the interest of time on trying to drill down onto a very specific question in traffic data that's relevant to transport, which is DDoS. DDoS isn't denial of service attacks. So this is a question where it sort of continues to loom. Why are we still facing DDoS attacks 35 years in? Because we're all still using the internet, because we have all these fundamental problems with the plumbing. So we did spend a concerted effort on just how much data sharing can we get, specifically on the metadata about DDoS. So big problem. So we did this paper, 17 authors. It's the first time I ever had this many authors on a paper. I thought, we are arriving as a discipline, because this is like physics now with 17 authors on a paper. It is a good sign, I guess. Some of that is because anybody who is willing to give us any tiny bit figment of data, you're an author, and also wanted lots of peer review internally of this work before we submitted it. So I'm not going to go into detail on that, but we really tried to investigate, what do the academics see about DDoS? What can we say about global? And there are some global macroscopic, like the telescope. The telescope can see artifacts of a certain type of DDoS. Honeypots can see artifacts of another type of DDoS. So if you take all the academic sites and join them together, not an easy trick, by the way. Academics are not that good at sharing data either. And it's not that they don't want to. Well, sometimes it's that they don't want to. But even when they want to, it's incredibly difficult. And the mechanism for detecting and inferring data, I'm going to skip over this. Is different. Everybody picks different parameters, different approaches, and they all have different vantage points, of course. So it's very hard to get a common view of DDoS. So we managed our expectations. We said, look, can we at least validate a claim that we see in the industry white papers? Like, there's tons of industry white papers in there. I'll just go back for one slide. In fact, a part of our project, and you might think this shouldn't be science. We actually could have did science on the industry white papers, which, as we know, are probably funded by the marketing department. But they are saying something about DDoS growth. It's all up and to the right. I mean, usually up and to the right, not always. And so there was a claim in there that a certain type of DDoS was dropping in 21 to 22, years 21 to 22. And we did manage to see a little bit of that. Actually, when they made the claim, it was 22. So the claim was DDoS is dropping. Our industry-wide efforts are being successful, which I think they were. Unfortunately, what we found is they increased again in 2023, this type of DDoS. And what I found is that the industry working group effort was very hard to sustain. And so it's sort of like people went off and had different priorities or left their jobs and such. All right. I'm going to say one slide on two-way traffic. So the two-way traffic is the holy grail. People want, what is really on the internet? This is like the plutonium of the internet, I guess. What is really happening on the internet? So we historically, until about 2019, had these packet captures of a commercial backbone link on the internet. One of our most popular data sets, besides the topology data set. Students wanted this data set. And then what happened to us every 5 years was the link that we were collecting data from upgraded to like 10 gig and then 100 gig. And we didn't have the money to build another monitor. And you cannot buy these monitors because it turns out people don't really measure the internet. Turns out people don't measure the internet in the way that a researcher might want a packet capture from the internet. They do lots of intrusion detection and filtering and flow statistics and sampling. If you want a packet capture of every packet for even 5 minutes, you cannot buy that off the shelf. You have to build that. And then this happened, and then COVID happened, and supply chains, and we had to get funding, and it took us 5 years. And so we're announcing we have a new 100 gig monitor of packet capture on the internet, and we're still doing the final, documentation and data set request form, because these are restricted data sets. We anonymize them. Then we also have you sign forms that say you will not try to reverse the anonymization, because that has happened in the past. So we have these multiple technical disclosure controls, policy disclosure controls. And our aim is to start sharing with collaborators. So you can see a little histogram of packet size distribution there. We publish statistics of all the packet traces that we've gotten over the years. And of course, the challenges here is, there's so many challenges. Getting the vantage points, even if someone agrees to do it, getting them to deploy it for you, or going up there, getting inside the rack that it needs to deploy it. So there's really no pixie dust for this. Well, there's approaches that have been more or less successful. I still say if folks want to do this, we have legal agreements to govern the use of the data. They're all online. Ours are all online. In fact, DHS had a big project 10 years ago that tried to do this, and we convinced them to put all their legal agreements online, and ours are based on there. So you now have open source legal agreements for sharing data, which is actually an innovation. But what usually happens, and I highly recommend it, is that if you really need access to traffic data, you have to become a part-time employee of the organization that has the data, because it really protects them. You have some protection there, and they have protection. And so that even works at UCSD. So students who are monitoring the UCSD network for security research are part-time employees at ITS. Maybe 0% time, maybe 1% time, but it's the legal agreement that matters. All right, so then we did spend a little bit of time taking another approach to sharing of traffic data, which is what people talk about a lot, differential privacy. We reached a stopping point with differential privacy. We declared some measure of, okay, here's what we're going to say, but really it was about the limits of differential privacy for asking the kind of questions that researchers want to ask about network traffic data and other kinds of network data too. So the real issue with differential privacy is how, in our context, is how can it protect corporate proprietary information while still allowing reasonable queries of the data? So we've submitted this little white paper on this. It's not on the website yet, but I can give it to you if you guys are interested. I am very interested in folks that are trying to use privacy technologies like this with networking data, and what the questions are you're trying to ask, or your users of your infrastructures, and what success you're having. Because I think there's a disconnect. And I think the funding agencies need help with trying to navigate that disconnect. All right. And then finally, DNS. I said I wasn't going to talk about this much. It's a whole nother talk. In fact, this whole talk I'm giving is a course. In fact, there is a course. I would say you can take it, but I taught it already, so it's not online. But all the materials are online. I'll talk about it in a second. So many more things can go wrong in the DNS, and do, than any of the other infrastructures that I've told you about. And it's even more resistant to any sort of oversight and governance. There's some oversight, but so I'm just going to mention there are two big data sets studying macroscopic properties of the global DNS. They're incomplete. They're the best we have. One is called DZDB. It's actually provided by a graduate student at UCSD, Ian Foster, many years ago, and he worked on this for many, many years and then needed help to steward it, and we offered to help him steward it. So we're kind of working on keeping this thing going together. What is it? It's a database of all the top-level domain files that he can find, either through the formal channels where I can share some of these top-level domain files, top-level zone files, like everything in .com, everything in .org, everything in .bank. And then it's a structured database. You can ask questions like, what name server dependencies are occurring with this domain over the last 10 years? And we've used that, and other researchers have used that kind of data to find macroscopic security problems with DNS dependencies and misconfigurations that open domains up to hijack of resolution. And then there's a big active measurement infrastructure which uses all this zone file data to probe every domain on the internet every day, or not every domain, maybe 60% of the domains, every domain they can get access to. And that's operated by some of our collaborators in Europe, and we've cloned some of that data locally, and then we have a bunch of other DNS data sets. So part of the reason DNS is so more resistant, there's a lot of money flowing in that ecosystem and a lot of private data, like PII data, like who owns the domain. So there's a lot of legal questions in there. Even getting access to the zone files is not seamless. There's like legal agreements going for every single zone file that the Internet Governance Organization sort of coordinates, but not seamless. Lots of consternation about that from folks that need this data to do actual operational security research. And then these are daily snapshots we get. So it turns out what we're finding now is that there's a lot of stuff that happens in between those daily snapshots, not recorded in the daily snapshots. And as you might imagine, any domain that lasts for less than a day, probably not up to any good. So those are actually the domains that are probably the most interesting to security researchers, because there may be a lot of other domains that did not get noticed and deleted, but have the similar properties as the ones that got deleted. And this is where, again, AI and ML can do a lot of work helping to detect the vast number of domains that are out there that are malicious. All right. So what we're going to advocate here, and we're still in the, justifying and designing prototyping, is something that was actually in place 20 years ago. VeriSign.com steward implemented something called Rapid Zone Update. See every update to the zone as it happens. This would be incredibly useful for security researchers who have been asking for this also more recently quite a lot, and some have proposed mechanisms to put it back in place. But it's going to require some policy agreement, some agreement by the industry that it makes sense to build some kind of zone of trust for at least the zones that want to be at a higher level of trustworthiness to opt in, maybe for now, to allowing access to these rapid zone updates. And I will say .gov, leading the charge in a bit. They are already, their zone has been public for a long time, and they're in the process, as part of a transition of who's their registrar, to allow updates every 5 minutes, allow access to the zone changes every 5 minutes. So that's on the right track. And we've talked with the folks who manage .gov, that's CISA DHS. We've also talked with NTIA that manages .us, and they're all very interested in having the US play a leading role in this DNS transparency idea. So that's less to report there because we're not on it. But if you have contacts at other TLD operators, especially around the world, come talk to us. All right, so how do you find all this data? We have this rich context catalog because we had researchers coming to us saying, I found the data, now what? Or I found the data, I don't know how to use it. What else has been done with this data? So created this rich context data catalog with not only indexes all our data sets, but all the papers that we know about. You're supposed to report your papers that use our data as part of the effort of getting the data, but researchers often forget that after the deadline, or after the camera ready deadline. So we do a bit of Google searching, and as much as we can. This is another thing it'd be good for AI to do. We're working on trying to get an LLM to figure out what papers actually did use our data, because sometimes they cite data, don't necessarily use it. So good job for an LLM. But you can get access to, you can start with the data set, find all the papers that use that data, find all the tools that can work on that data. So it's a really useful research for students, faculty. And then we actually have a course, because once you even find the tool, you may be like, all right, I need a little more help. So we created a course, Internet Data Science, Network Infrastructure Data Science. All the stuff is, all the slides and readings and everything is online. Except the videos. I didn't do the videos of the class online. It was the first time I taught it. But what really came out of that for me is, we need help from the UCSD machine learning platform, which you heard about yesterday a little bit. And Valerie and somebody are going to give another talk about it this afternoon at the NRP thing, which is, can we get a lot of these data sets integrated into the platform so that students can have access to these terabyte data sets about the real internet for their research and even their course materials. All right, and then we do a bunch of meetings that really feed into all of the things that we're designing, and then we have a bunch of people that are using the data now. So that I'm going to skip over these data sharing stats. These are all on our website. Lots of people using the data, different types, different countries. Lots of ML AI related requests. This is just because of this week I added this. Who's actually using our data? Who actually mentions ML AI or something related in their data request? Because you have to say approximately what you're going to use the data for. specific use cases for the kind of data that seem to be most getting used for LLMs. And then just a few projects I came up with which I would really love to have done. In fact, some of these SDSC is helping us with now because, as I mentioned at the beginning of the talk, low fruit, it's not low fruit, but it's, let's say, ripe for innovation, ripe for transformative advances, would be problems that you could really bring an LLM to bear on. Internet, infrastructure, security-related problems. And now I think this is perfectly queuing up our pit stock, at least I hope so. Summary, we can help you with data, tools, resources, curriculum, all the users of your platforms, I hope, or students if you have access to them. And you can help us deploy the VPs, peer with the infrastructure that we have, and give us feedback on data sets that you use or data sets that you want. Give us a try. We will do our best. Sorry to go over time. I'm done. Thank you.
Yeah, so we started a little bit late, so we have time for maybe 5 minutes of questions. If anyone has questions, they can come down and ask down to the microphone. Nobody? No.
Hey, so I'm Mike Sherman from Chameleon and University of Chicago. We spoke briefly, but I wanted to ask, for your measurement points, what are actually the requirements for a device or a location to be a good measurement point?
It's good if you're connected to the internet. It's good if you're really connected to the internet. So, a test bed that is only connected to other test bed nodes, not so interesting to us. And then it's good if you're connected to the internet in a place that we don't already have connectivity. So unlike Ripe Atlas, where they can just take a box of these things and throw them up in the air at a conference and get 300 new nodes, we can't because there's it's much more automated than it used to be, but there's still a manual company. There's a cost to every deployment. So we don't want 100 nodes in one zip code. Unless it's 100 different ISPs. That would be great if there were 100 different ISPs in one zip code, but no. We want topological diversity, different ISPs at the access point, and geographic diversity. But every node on all of the test beds, I think, would be a totally fine addition to where we are. In fact, one of the things we like to do is create teams of ISPs. So you could have a fabric team and see how much topology of the internet it can see. And a NRP team and a Cisco, a Comcast team, et cetera. And we have a little bit of that going on because we have some of these commercial collaborators deploying nodes for us right now. So the answer is yes.
Okay. Yeah. And
in terms of hardware and like power and all of that, it's on the website. It's very low rate. We are not Z-mapping the internet. 100 packets a second. I hope that doesn't sound like a lot. It's nothing. Sometimes we go to 200. So it's a very small amount. It's very slow rate. So we're not giving you a snapshot of the internet in 40 minutes. No, it's probably a day. We can do V4, V6, whole nother question. And then we have these teams. So different teams are doing different. There's currently about 160 nodes, 157, I think, this morning. And so different nodes can do different experiments. And what we're trying to get to as part of this design effort is allowing you to say, I'll allow this experiment, but not that experiment. But as you can imagine, there's a whole complicated policy layer in there of how to execute that best. So very little, there are Raspberry Pis, very little power, 100 packets a second. It's great if you can have remote hands. You can sometimes kick it if we need a kick, but very similar to what I think Floto probably needs.
Mm-hmm.
Okay, Kees de Laat, non-US researcher. I appreciated your talk. So you started out with AI and your entire data and measurement. So I was wondering, do you also want to use AI and large language or large action models to interpret the data? For example,
yeah. In fact,
large action models do objects and relationships. And that could give you information about causality. Like this is happening here and has a relation with something that you see elsewhere.
Absolutely.
That is the most interesting part, I think, what we can do here.
Yep, you can. In fact, again, researchers are working on this right now. It's a little traumatizing and very humbling to take work that you spent 2 years on and go ask ChatGPT to solve the problem, and then it just solves it. And you're like, oh man, all those regular expressions we made for naught. So I think this infrastructure property classification is kind of what you're talking about, and it's whoa, what did I just do?
Well, there's also object types and relationships between objects, and you can turn this in objects and relationships relationships. So large action models is apparently the new hype.
Okay.
And that takes it one step further. We can talk about it in the break if you wish.
Yeah, I would love to. I'm assuming takes the language, takes the LLM and turns it into proposed actions to take.
Yeah,
Is that
it identifies objects and their relationships.
Yep.
So it goes one
Yep.
step beyond LLMs.
Yeah.
LLMs is just what is the next word, probably given the past text. But
Yes.
this is about objects and relationships, building graphs,
Yep.
but then action graphs. So this would be probably very beneficial for the enormous amount of data you have.
Yes, indeed. I also want to do a shout out to another project called Internet Yellow Pages, which is trying to do this without LLMs. And I really hope that any use of LLMs would consult the more heavily curated forms of these graph data, because sort of throwing a bunch of unstructured text or even structured text that may not be perfectly accurate about internet infrastructure, and then having actions about the network come out of it, like what could go wrong? And I think ARPIT's going to probably talk about that. I hope ARPIT talks about that. But nonetheless, in terms of what researchers do, which is heuristic inference of properties, including security properties about internet infrastructure, I absolutely 100% agree. And the fact that proposed actions could come out of an ALM, which I'm not familiar with that technology, and then could be vetted, aces, yeah.
Okay, look up LAM.
LAM, I'm on it.
Hey, Casey. Kevin Thompson, NSF. Can you go back to the last slide where you showed a little cloud of industry collaborators? Could you just say a few words about what you're doing with those
This
four?
is an incomplete list. I had another slide. So some of these partners, well, actually, if you talk about many of the industry partners have deployed infrastructure for us. Some of these partners have used our telescope data and asked for help using the telescope data. There's some partners in Farsight right now is actually owned by, it got purchased by Domain Tools. So Domain Tools is an industry partner that provides access to us of their data sets and also uses the telescope data. So there's like a quid pro quo. But we also have a lot of other industry partners. Gosh, I wish I had the other slide. I deleted the other slide. Who are providing us access to their data sets, like commercial data, net acuity for geolocation, IP info for metadata about IP addresses, the CLLI stuff, iConnective for access to the CLLI silly codes, that's proprietary data sets. So we actually do have pretty good luck getting data, commercial data from data companies that, so we don't have to pay for it because these can be very expensive data sets. I think the CLLI data is like $100,000 a year. It's just out of our reach. Right now, Kentic is really, they've been a partner with us all along. So they were part of the ones that were talking to us about what it would take to really share traffic data. Kentic is the traffic observability company. They've given talks at some of these meetings in the past, I think. And so they do a lot of flow data, sampled flow data. They've also used our telescope data in the past to test out their tooling. When we actually had an employee that ended up working at Kentic, two employees that work at Kentic. And they've had many conversations with us about the whole differential privacy and how could differential privacy help with them sharing data with researchers, because they are interested. Kentic would love, and other companies like Kentic would love to see a state of the internet report come out of data that they have access to. They are a measurement company, so they don't own the data, right? They're like the NetFlow guys that have their customers are the ISPs. So they have some agreements with those customers that allow some research on the data, but sort of nothing like what HIPAA allows with our medical data yet, right? So part of the conversations that are happening are, how close can we get to the data? Will it require that somebody becomes an employee of Kentic? Not a terrible solution. Like, I think we have to confront that this will be like, it'll be a 0% or 1% employee. We have to confront that navigating these legal waters is going to require some policy innovations as well, because the data is sensitive. And we don't want all our data being handed out with no governance associated with it. Well, wait a minute, it kind of is. Okay, never mind. That's another talk. But in terms of traffic data, I think the sensitivity associated with that is entirely appropriate. And I think part of the reason that we have stalled progress for so many years is that we want it to be a technical solution. It's not. It's not only a technical solution, but obviously technology has a role to play. I'll give you a more complete list of industry partners. I think it's on our website. Did I leave anyone out? Coalition was using telescope data.
Right.
Okay, we're late.
Okay, I have another question, but it's more in line with Mike's question, so maybe I'll take it offline. But it's more or less, what can Fabric do to help? But we can
deploy measurement vantage points, I
that's what
think. Yeah.
And maybe, the another thing is maybe to make
And
the
Fabric
data.
does, do you guys have connectivity, forgive me for not knowing this, at internet exchange points? Like internet exchange, like StarTap and the R&E exchange points? Because that would be a really good place. We're prototyping our IXP deployments at R&E exchange, or at least nonprofit research-friendly exchange points like CatIX, INEX, SF mix. So if Fabric has connectivity at those places, that would be you could provide a conduit there for deploying a node and then peering with the non.
Yeah, we'll have to talk about it and see what exactly you want. But yeah, we in fact are our own AS for IPv6. So
Right,
that's another
and
thing
peering
too.
with Gillnet, peering with like we can do low fruit and then start.
Yeah. So there's a lot of opportunity, but
A lot of opportunity.
in the interest of time, let's
Yeah.
thank
Thank
Casey.
you all so much. I'll be around.